Okay, I think we'll get started. If you're just coming from the G&L project, I encourage you to go back and look at the intro to this playlist and see if this is the right series for you. Otherwise, we'll get started with talking about forces again. We talked about that last time when we introduced Newton's first law, and we've got two more to go. Now we'll introduce Newton's second law, also dealing with forces. All three deal with forces. As we saw that forces were a fundamental concept with how we're developing our physics here now. So the key idea of Newton's second law is that forces cause acceleration. So if you have a net force on an object, it will accelerate. And so this is coming off of Newton's first law, that in the absence of a net force, an object in uniform motion will stay in uniform motion. So the second law then kind of says that if we apply this force, it's going to cause an acceleration, and the second law tells us exactly how that will cause it, and that is according to F equals ma. So this when you say Newton's second law, people will just immediately think F equals ma, and that's the mathematical expression. In words, which is an object that has mass will undergo an acceleration when subject to a force. Now this force, we have to be careful, is the net force, and so it's the vector sum of all the component forces. So we've been learning about the different types of forces, so it'll be key in identifying all the forces that are on a object. And a key bookkeeping helper for that is something called the free body diagram. And you can get yourself so far in physics if you first draw a cartoon picture, as we've talked about, and then take that cartoon picture, turn it into a free body diagram. So on these problems that are coming up now, if you get stuck, if you can just get yourself to the free body diagram, that can usually get you going. So really, really important to learn about free body diagrams. I'll go through just a little bit here, and then we have our in-class worksheet. So those of you in the G&L project, see if you can find some worksheets out there on the internet, or have ChatGPT or Gemini help you with some. Okay, so let's see how these free body diagrams work. So let's take an example, and this is going to bring up a new concept, the concept of the normal force. So I'm just standing here on this floor, and I'm not moving, right? So I'm at rest. So according to the first law, I must not have any net forces acting on me. Also, according to the second law, I must not have any net forces acting on me, because if I did, then I would accelerate, and I'm not accelerating. But clearly, I have mass and I have weight. I'm standing on Earth, so I have a weight force pointing downward. But that is pressing me against the floor, and the floorboards here are pressing up against me, and they are providing just as much force as they need to completely counteract my weight force. So if I was heavier, if I put my backpack on, the floorboards would have to apply more force. If I lose some weight, then they'll apply less force. That force that's being applied is called the normal force. It is a contact force, and it gets its name because it's always normal to the surface. So we have these categorizing of forces, and we haven't mentioned this normal force. It's a little different category sort of by itself. But whenever two objects, when two objects are in contact, we can call the force here applied against this guy as the normal force. So the floor, if I'm the object here, the floor is applying this normal force. So let's draw a picture of us. This is a very simple system. I'm just standing there. Let's draw a picture of that case. So the first thing we want to do is draw this cartoon picture. And then with our cartoon picture, what do we have? What do we know? So we know the various forces. So I have a weight force, and now I have this normal force, as we talked about, and that normal force will just counter that weight force. But the normal force can only act normal to its surface, right? So the normal force has to be pointing straight up from the floor. So then comes the free body diagram. So what you do is you take the mass and you make you just make a circle here representing the mass itself. So you can press it down to just a single point, and then you draw the force lines on here, all of them. And then you see what's going to happen. this exactly counters that. So that means if we draw the vector sum of this, we end up right back at the beginning. So the net force here equals 0. And if I'm standing here, nothing else happens, I should just remain here forever, because there's no net force acting on me, so I will not accelerate. I'm at rest, my velocity is constant, happens to be 0, so therefore it will stay constant forever. All right, let's look at another couple of examples here. We'll do two and one here. So we'll look at this example. We're going to pull a box across the floor using a rope that's attached to it. In the first case, we'll pull it at a constant velocity. So the box is moving at uniform motion. Acceleration is 0. So this tells us when all is said and done, we better have a net force of 0. Now notice here I was the object. Now clearly we're thinking about the box, right? So we identify the box as the object, I'm the agent, and we have this rope attached to it. So let's take the box, right? The box becomes just this circle. So we reduce our cartoon box down to that circle, and we identify the forces. So there's a tangent force here, right? So that's this force. It's always in the direction of the rope. There's a weight force, of course, and there's a normal force. And then there is a tangent friction force opposing the motion. And so this is our free body diagram. And then the question is, well, what are all these lengths? Now, if this is a type of problem we'll be asking. Now, we'll have to, of course, know 3 of them to get the 4th one. But we know that if we know 3 of them, the 4th one has to be the vector such that when we add all 4 of these vectors together, we get back to 0 because we want no acceleration here. And I think this can get, it seems simple at first, but it can get really confusing. So definitely now as we go through the worksheets and you're listening to this and then you get some practice, really push yourself on these ideas. Okay, now, so that'll have a net 0 force. So let's look at one thing in particular. Over here, the normal force and the weight force were equal, equal but opposite. So the magnitude of the normal force equaled the magnitude of the weight force. That isn't the case here because there's a component, there's a Tx component that's pointing upward, right? That's helping the normal force. So the normal force is actually less than the weight force by the amount that the tension is helping, because the rope is at an angle, so it's lifting up the box, making the box feel lighter against the floor, so the normal force from the floor does not have to be as high. And then the frictional force is not the same length as the tangent force, because the tangent force is at an angle. Some of it is going into lifting up the box, and some of it is going into pulling the box along the floor. And so the x component of this, oops, this is ty, tx component of this, the tx component is equal to the magnitude of the friction. Now let's have an acceleration. So let's say we're pulling on this and we're going to pull it, we're going to accelerate it across the floor. Then our tension becomes much bigger. It causes, if we were to add all of these together, so let's do that. So we have down with weight, up with normal force, not quite as high, over with friction, and then a big tension. Then our net, here's where we started, here's where we finish. F net, right? And actually probably I have that. So here we've pulled it so much that we've actually pulled it off the floor. In this case, the way we've drawn it here, what likely is happening is that the normal force, it's like if we pull it hard enough to accelerate it but just not rip it off the floor, then the normal force will be enough to allow for this to cancel enough of the weight such that this points straight this way and it slides across the floor. But in the general case of just accelerating by just ripping on that rope, In this case, it's telling us we're going to be pulling it up off the floor even. Okay, let's look at this case of the cart sitting here at the top of this ramp. Now, free rolling wheels, no friction due to drag. We'll ignore drag. And here's where this idea of the normal force coming in always perpendicular to the surface plays a big role. So let's draw the free body diagram here. So we've got the free body diagram. We've got a weight force that points straight down, right? The weight force is always pointing down. But the normal force, all it can do, the only thing it can do is point perpendicular to the surface. So it can only go off in this direction. So when we write, no matter what it does, whatever n does, it's going to have a little x component where the weight does not, and thus the total net force is going to be pointing down the ramp. And so what does this free body diagram say is going to happen? It's going to say the cart is going to accelerate down the ramp, which we've already done a lot of problems like this with the cart accelerating down the ramp. So we would hope that when we talk about it in terms of forces and free body diagrams, we get the same result as what we were getting earlier when we were doing the kinematics of the cart rolling down the hill. Okay, and then the final example. Let's just think of a car driving down the road at constant velocity. And this can be, this case where this can be a little confusing. So it's confusing in trying to identify all the possible forces. So we're told here the car is moving at a constant velocity. So what does this mean? It means right away we need to write that acceleration is 0. Okay. Now, let's draw our free body diagram. The car is not going up or down. Thus, our weight force and our normal force are equal but opposite. So our car is not accelerating upward or accelerating downward. We have no net upward or downward force. It's definitely feeling a lot of air resistance, right? That's one of the biggest things that consume the gas mileage is the air resistance. So we have a drag force opposing motion. Now, let's say we stopped here. These are the obvious forces. If we look at this free body diagram, it's telling us this must be experiencing acceleration in this direction. In which case, the car would be slowing down, right? But it's not. We're saying it's a constant volume, and we certainly experience this. You can drive all the way across the country at constant volumes, or constant velocity. So there must be a force in this direction, right, pushing the car in that direction. And so what is that? Well, sometimes we might just label this as F car, okay, or F motor, something like that. The car is providing, via the motor, the necessary force to keep it going, even though it's facing this strong drag resistance wanting to slow it down. What is the origin of that? It's actually a frictional force. Imagine if we could lift the car, if someone just came and grabbed the car and lifted it off the ground, the wheels would just spin, right? And if it was moving this way, it would just slow down because it's in the air. So the fact that the wheels are in contact with the ground allows the car to have this F car moving in this direction. And so let's think about it for us, just us. If we're standing still and we take a step in this direction, we've gone from rest to moving, so we're accelerating. Well, how are we doing that? Our shoes are pushing against the floor, right? There's a frictional force between our shoes and the floor. If we're on ice, our feet just slip out and we don't actually move. We need the frictional force to propel us this way. And this is why it's a little confusing, because we think of frictional force as always opposing motion. What's the motion? Our shoe wants to push things this way, right? So the frictional force points this way, which moves our whole body because the floor is attached to the building, which is way, more solid than we are. So when we push against that, we get pushed this way. And so this is actually a frictional force. So those frictional forces, those contact forces, can be hidden when you're looking for them in free body diagrams. All right, so now it's just a matter of practice, and as I mentioned, boy, if you can get good at your free body diagrams, then that will make you much, much stronger when it comes to the type of questions that are going to be asked now in the coming days.